We're on. We're recording. So we're going to start just by talking about NMR generally. As I've detailed in the booklet, you don't have to know how NMR works in order to answer the questions on it, but a little bit of understanding, I think, helps. This idea of spin, particles can spin in different directions, opposite spin. And all nuclear particles can do this, all protons and neutrons can do this. If you've got an even number of nuclear particles, then the spin will cancel out. If you've got an odd number, protons, just a hydrogen atom only has one proton, or if you've got a carbon-13 nucleus, that odd number of spins means you get some residual spin. And apologies to the physicists if I've got that wrong, but the spin generates a magnetic field, and so we tend to talk about spin up and spin down when we're talking about the states of the nuclei. Again, you don't really need to know that, but it sort of explains why I'm going to be drawing arrows on the board when I'm talking about the states of different nuclei. What we can do then is impose a magnetic field on our sample, and the up and down states will tend to split in terms of energy, with some of the nuclei lining themselves with a magnetic field and some of them opposing it. And the difference in energy can be translated into a frequency in the electromagnetic spectrum, and it's the radio frequency region, which I'm sure you know from your physics is a very low energy part of the spectrum. It's the lowest energy part of the spectrum because it's a tiny energy gap. So we can then put some radio frequency radiation across our sample, and then some of those particles will flip their spin, which absorbs a tiny amount of energy, and then they usually drop back, and that going up and down thing is the resonance. So hence nuclear magnetic resonance spectroscopy. That's where all that comes from. As far as you're concerned, we draw a spectrum where we look at the frequency of absorption of the radiation for the different protons, and different protons in different environments will absorb radio frequency at different frequencies, and they can be plotted on a graph. So we end up with a sort of series of peaks on our graph, where each peak represents a nucleus, a proton or a carbon-13 nucleus absorbing at a different frequency. For reasons that I don't really want to go into, the scale here is, it's not actually in frequency units, it's a dimensionless scale in parts per million. If you could just accept that, that makes it easier. And for reasons that I've never quite understood, the axis goes to the left. Don't know who came up with that one. That seems to go against everything we've ever done in any other graph ever. But 0 on our NMR spectrum is always at the right. And then we go up to the left. So we have different values for the different frequencies of absorption, and they're referred to as chemical shift. So the first two important parts of NMR is that each atom in a unique chemical environment generates a peak, and the chemical shift, as it's called, of the peak gives us information about that environment. that's the easier bit of NMR to understand. This is sagging. Yep, it's doing a thing. I need to tighten a bolt somewhere. Okay. Okay, so far? Okay. So if we look at a spectrum, there's lots of examples in your book, but let's just pull some up. That will do nicely. Staying up, is it? Oh, it's that. Okay. Should learn how my own camera works. There we are. Right. Good camera. Stay still now. Right, so this is a spectrum of 1-chloropentane. Which I've just pulled up. So we've got our axis along the bottom, the delta scale as it's sometimes called, or the chemical shift axis along the bottom. I've got 4 peaks. Or slightly varying heights, but for carbon spectrum we don't have to worry about the heights, it's not important. What we notice is that there are 4 distinct peaks, and there are 4 distinct peaks because we've got 4 distinct chemical environments. We've got the carbon that's next to the chlorine, we've got the carbon that's next to the carbon that's next to the chlorine, we've got the carbon that's next to the carbon, next to the carbon, next to the chlorine, and then the carbon that's right down the other end. They're all different. There's no symmetry in the molecule in any way, so we get 4 different peaks for 4 different carbons. And then they're kind of spread out. The left-hand peak there is at about 44. So you're always going to have a set of chemical shift data. It's printed on the back of the booklet, but you get this in your AQA data sheet on the back of your periodic table. So the left-hand peak there at about 44. Notice that it's out of the range of a kind of an ordinary carbon. These are just ordinary alkyl carbons on the left. At 44, it's nearer the, well, there's a range of 10 to 70 of carbons that are next to a chlorine. So that peak on the left is the carbon next to our chlorine. And the reason it's shifted is because, as I'm sure you know, chlorine's an electronegative atom and it withdraws electron density from around the carbon, and taking that electron density away changes the field, the field intensity around that particular carbon. So we often refer to that cloud of electrons around an atom as shielding, don't we? So if we take away that shielding, we say that the carbon is de-shielded. And on our spectrum, anything towards the left is more de-shielded. In other words, it's got more electronegative stuff next to it. We also notice, if you look at the shift, the chemical shift data there on the back of the topic booklet, that anything with a double bond is also shifted further to the left. And then things with double bonds that are also next to an electronegative atom, like esters and acids and aldehydes and ketones, are the furthest shifted to the left. And that's the same for proton NMR or carbon-13 NMR. So that carbon there, carbon A, will be that peak on the left there, and then presumably as we get further and further from that chlorine, we get less and less shifted, less and less de-shielded. Okay. Okay, so the point I put at the top of the screen there, which is very important, is this idea of unique chemical environment. Let's have a look at this spectrum. This is a proton spectrum. So we're looking at the hydrogens in the molecule now. And it's the proton spectrum for propanone. So we've got 6 hydrogens in propanone. So we only get 1 peak. So what's going on there? Well, what's going on is that we've got a certain amount of symmetry in the molecule. The molecule's kind of symmetric either side of that carbonyl group. These CH3s and these CH3s are in the same chemical environment. And of course, all the H's in that CH3 are in the same chemical environment as well. So all 6 hydrogens in that molecule are in the same chemical environment. So in terms of unique chemical environments, we've only got 1. So we get 1 peak. And if we look at the chemical shift again, that peak is at about 2.2. So 2.2, if you look on the table B, the proton NMR chemical shift data, 2.2 corresponds to that hydrogen. Notice it's slightly bolded. Yeah, we're looking at that hydrogen there. That hydrogen next to a carbonyl group is 2.1 to 2.6. So that's pretty much bang on the money at about 2.2. So in a way, we don't get a huge amount of information there. When there's a lot of symmetry in the molecule, the spectrum becomes quite simple. So think about a spectrum of benzene, for example. How many peaks would we get in the carbon-13 or the proton NMR spectrum for benzene? What do we know about benzene?
Is it 1?
We get 1. Because one thing we know about benzene from the last topic is that all of those carbons are equivalent. There's no single bonds and double bonds. There's just that pi cloud sitting over the top of the whole thing. So all the carbons are equivalent, all the protons are equivalent as well. So we'd see 1 peak in both the carbon-13 or the proton spectrum. Okay, let's make it a bit more interesting. What if we had a benzene ring, but we put something on it? Say a chlorine. Just have a think about how many peaks I would see in, let's do carbon first. How many peaks would I see in the carbon-13 spectrum for chlorobenzene? No, I haven't got chlorobenzene in mind. How many peaks do you think?
4.
4 is right, yeah. So we'd have a unique carbon there. That carbon there would be the same as that carbon there because they're both they're both next to the carbon chlorine. As we went round, these two would be the same as well. Not the same as those two, but the same as each other because they're 2 carbons away from the chlorine. And then we'd have another one at the back there. What about the proton NMR? How many peaks would we see for that? What do we reckon? Do you want to have a guess?
Yeah.
Remember that we don't have a hydrogen here because the chlorine's substituted the ring, but we'll have hydrogen sticking out all of the other carbons. So there's 5 hydrogens there. These 2 will be equivalent. These 2 will be equivalent, and then that one will be on its own. So we've got that line of symmetry going through our molecule there. Will give us 3 peaks. Okay. Have a fiddle on paper at trying to come up with a structure for this molecule here. It's C6H12 is the empirical formula, and it's got 2 peaks, and one of them is quite a long way down. And this is a carbon spectra. You can tell the difference between carbon and proton, by the way, by the chemical shift. Carbon 13 goes up to about 200. Proton spectra goes up to about 11 or 12. So if it's going up to 200, it has to be a chemical shift for carbon. So that's carbon 13 NMR for C6H12. Just have a think, draw some structures. We've got 2 peaks, one of them at around about 120 something. Okay, so most people have worked out that with a peak around about 120 something, given that it's C6H12, there has to be a carbon-carbon double bond. So let's start with that. Then we've got 6 carbons to account for, but we've only got 2 peaks. There has to be a lot of symmetry in this molecule because I've only got 2 different types of carbon in there, and I've already used 1. So if I put another type of carbon in this molecule, every carbon, all the other carbons, the other 4, have to be in that same environment. We had an answer over at the back there.
Just 4 methyl groups.
That's right. If I put 4 methyl groups on like that, that gives us a lot of symmetry, because we've now got symmetry that way and that way, which means all the CH3s are equivalent. So I'll get 1 peak for the CH3s, that's the big peak there, and 1 peak for the carbon-carbon double bond carbons, that's that peak there. The difference in size of the peaks might suggest I've got more of this carbon than of this, which is true, but for carbon 13 it's not reliable. You can't really go on peak heights to give you information. In proton NMR you can, and we'll come to that later in the lesson, but yeah, peak heights for carbon is not very reliable. All right, let's just have a look at something else. No, maybe not. Okay, that is C3H8O, which kind of narrows down its possibilities, but if you could narrow it down a bit more for me. So this is perhaps a little bit simpler, but I've put it on just to illustrate a very important point. And if you get this point, then you've really understood the first part of the lesson. We've got 3 peaks and we've got 3 carbons. So all of those carbons must be in different, unique chemical environments. Would anyone like to tell me what the structure is? Or the name of it? Yeah. Why does it have to be propan 1-ol and not propan 2-ol? After all, they both have the same empirical formula. Because right, there would only be 2 different chemical environments. If I put the OH in the middle, I've got a line of symmetry. I mean, it's not quite a line of symmetry because it's tetrahedral. But the important thing is I've got 2 methyl groups attached to the same carbon. Wherever I've got 2 methyl groups attached to the same carbon, they're both in the same chemical environment. So this molecule would only give us 2 peaks. So it has to be propan 1-ol. Okay? It's a very standard part of the AQA of AQA's kind of question system, where number of carbons it makes a good multiple choice question actually. They'll give you a molecule and just ask you for the number of the number of peaks in that environment. So the number of unique chemical environments for carbon. Again, using a bit of chemical shift know-how, we can see that so on the thing here, so we've got, is that way around? That H on a carbon next to an oxygen, sorry, I'm not looking at H's, am I? It's carbon spectrum. That carbon next to an oxygen is 50 to 90. We're kind of right in the middle of that with about 64. Okay, so again, right on the money. So that C is that peak there. The middle carbon is presumably that one, and then the CH3 at the end would be right down on the right-hand side, the least shifted. Okay, I'm going to hit pause on the video now, and I'd like you to have a look at exercise 1.